Good morning, good afternoon, good evening. My name is Zabari Sobers, third year electrical engineer.
My name is Sovereign Wooten, third year computer engineering.
My name is Kevin Littles, a third year electrical engineering student.
And this is our aircraft pitch control presentation for Dr. Moses Anubi. So firstly, we're going to go over the tools used. We utilized MATLAB's Simulink program. This was used for processing and generating our waveforms. Secondly, we used our transfer function provided to us by Dr. Anubi himself. Thirdly, we utilized our two input waves. These were our sine and our unit step function waves. These were used in order to see how our transfer function would interact with them for our outputs. Next, we utilized our PID and our adder. These were implemented in our closed loop implementation. We'll get into that later in later slides. And our oscilloscope was used for viewing our wave outputs. So project description. Our goal for this project was to take our input waves, observe the effects of our transfer function, and look at the output, basically. So we utilized two implementations, one being our open loop and one being our closed loop. Open loop would give us an underdamped response. This will be discussed next slide for both our sine and our unit step function waves. In our closed loop, we utilized the PID and the adder that provided us feedback. Our man, Mr. Sobers over here, will give us more insight on that closed loop later on. So our dampness responses, these are underdamped response. This will give us some overshoot. This is the least efficient method or implementation. It'll give us our overshoot right here. As you can see, it'll overshoot the equilibrium point, and then it will, begin to oscillate and eventually level out about our equilibrium point. Not efficient. That's our open loop implementation. Our closed loop will give us the critically damped response. This is the most efficient way to get into our equilibrium point. This is the desirable position.
So now we'll go into our PIDs. PID stands for our proportional integral and derivative controller. The controllers are just simple implementations of feedback. These guys can eliminate and remove steady state errors and anticipate future outputs. So our proportional action is just as simple, proportional to the error control of the wave. The integral portion, it offsets error and is eliminated by this control. Its main function is just to make sure that the process output agrees with the steady point and the value in the steady state. Our derivative control makes our system improve the closed loop stability and also improves the transient response. These PIDs are widely used. These guys can be used for pressure, the speed flow, and the temperature and automatic control processes.
See, next we're going to talk about the design of our open loop. First, we chose the sine wave. Our open loop system is often used for signal processes or building blocks in more complex control systems. So first we chose the sine wave, and then we had it going to our transfer function, and from that we had it going to our oscilloscope, and it gave us this wave right here. As you can see, from peak to peak, this peak is higher than this one, and for the result of that, that's basically saying the plane is still on the upward motion of going up in the air. Next, we did an open loop for sine wave. As a unit step input is a sudden change in the system output. We exhibit a transfer response characteristic by overshoot, sailing time, possibility oscillations depending on the system and characteristics. So basically, we just changed the sine wave to a unit step function wave, and we still had it going to our transfer function and going to our oscilloscope. And this is a better visual of you looking at it, of it still increasing while going up in the air. And then next we have our closed loop sine wave. So our closed loop system, the output is constantly compared with a reference signal, and the output wave of the closed loop system may exhibit various characteristics depending on the system dynamics and the properties of the input signal. So for what we did, we basically added an adder and added a PID, and then we still had that same transfer function, but now we having it feed back into itself, constantly changing. So this is where we have for our underdepth, and it will lead into back to oscillating in the next slide.
So now that we have our closed loop for our unit step function, as you see, as Kevin said, that this PID and this adder will consistently be giving feedback to the unit step function that will give the output for the oscilloscope. So if you see here, you will see that the unit step function will gradually rise to its peak around 3 to 4 between 3 and 4, and then start to level off at that equilibrium point. So if you can see that the troughs from peak to trough, they are going to slowly reach equilibrium. So that would be it oscillating right about the equilibrium point, making the critically damped response that we're looking for. So in conclusion, this project just showed us how the transfer function and PIDs interact and alter the unit step, alter the unit step function, the sine waves. With the PIDs added to to form the closed loop, the pitch angle is found through the adjustments using the feedback that is generated. So the importance of the damp responses that change the open loop from the underdamped to the closed loop that gives us that critically damped response, which will in turn make flight safer. Any questions, comments, concerns? Thank you. This is our presentation project. Thank you, Professor Newton.